Hello and welcome back to Advent of Code 2014. We're on to day 15. We're halfway through the month. It's been pretty interesting so far. I mean, this ink code thing is quite interesting because it builds up. This hasn't been done in any previous year that I've done before, where you have a program and you continuously modify it over like half the days. So, 15. Oh, of course, here we go. It's an int code problem. So the last one was 13, right? So that's the one we'll reuse. Okay. All right, I'll just grab my coffee and let's start on day 15 then. Okay. Day 15, oxygen system. Out here in deep space, many things can go wrong. Fortunately, many of those things have indicator lights. Unfortunately, one of those lights is lit. The oxygen system for part of the ship has failed. This reminded me of Faster Than Light, the game. According to the readouts, the oxygen system must have failed days ago after a rupture in oxygen tank 2. Oh, this is very faster than light. That section of the ship was automatically sealed once oxygen levels went dangerously low. A single remotely operated repair droid is your only option for fixing the oxygen system. Okay. The Elves care package included an int code program, your puzzle input, that you can use to remotely control the repair droid. By running that program, you can direct the repair droid to the oxygen system and fix the problem. The remote control program executes the following steps in a loop forever. Accept a movement command. Send the movement command to the repair droid. Wait for the repair droid to finish the movement operation. Report on the status of the repair droid via an output instruction. Okay. Only 4 movement commands are understood. North 1, South 2, West 3, and East 4. Any other command is invalid. The movements differ in direction but not in distance. In a long enough east-west hallway, a series of commands like this would leave the repair droid back where it started. Okay. The repair droid can reply with any of the following status codes. 0 if they hit a wall. 1 if they've moved 1 step. 2 if they've reached the oxygen system. Okay. You don't know anything about the area around the repair droid, but you can figure it out by watching the status codes. For example, we can draw the area using D for the droid, hash for walls, dot for locations the droid can traverse, and empty space for unexplored locations. Then the initial state looks like this. To make the droid go north, send it 1. If it replies with 0, you know that location is a wall and the droid didn't move. So if you What is the fewest number of movement commands required to move the repair droid from its starting position to the location of the oxygen system? So once we know where the oxygen system is, then it would just be breath first search, wouldn't it? Okay. Well, so in each step we kind of just want to find the nearest unknown location. It's an infinite grid, is it? Okay, so fine. The only thing we need to deal with is we would have to, because it's an unbounded grid, so it'd be initialized with like no locations, but we could put a bunch of unknowns. Okay, right. I have an idea. So we need to import encode. Okay. Okay, so let's say position equals 0, 0. There's no notion of direction. Actually, there is, sort of, but we don't store a direction for the robot. Okay, so we've got when we've decided which way we want him to go. Well, okay, so let's say we have grid equals default dict int, so everything is 0. We'll use 0 for empty space. No, 0 for unknown. Yeah, 0 for unknown. Let's just make a note here. 0 for unknown. 1 for floor. 2 for wall. Okay. Okay. And then we need a couple of helper methods. So define get neighbors of a specific position. For delta in, let's say, -1 0 1 0 0 -1 0 1. Yield P0 plus delta 0 P1 plus delta 1. Let's define distance between P1 and P2. Returns, it's going to be the absolute value of P2 0 minus P1 0 plus the absolute value of P2 1 minus P1 1. So that's distance. What else do we need? So put this down here. So we need to put some stuff in the grid, some unknowns, because it's completely empty. Well, position 0 0 is a floor. So grid dot add pause. Wait, grid pause equals 1. And we need to initialize all the things around it. So for neighbor in get neighbors pause, just do this. Grid neighbor. This seemingly does nothing, but it creates the side effect. So the IDE complains, but I believe it should have the side effect of adding those to the grid if they're not already in there. That's the key. So we're not overwriting anything, but if it's not in there, we set it unknown. So if we do that step there, okay, so while true. In every step, we want, okay, so we need to initialize the int code. So it's just going to be like this. Okay. So for each we need BFS here. So BFS is just going to tell us the distance to a goal and the next step to take. Because for all we know, they could make a maze and then you have to wind around to find it near goal. All right, so BFS. So it's just standard BFS. So we do Q import Q. Q equals Q dot put start. So we want dist equals distance table. Oh, we're gonna need a came from map as well. All right, well. Okay, so while Q dot while not Q dot empty current equals Q dot get all right, so for neighbor in get neighbors of current. All right, if neighbor in dist, skip this one. If neighbor, if get neighbors, no, if, all right, well, this needs to be up here. If rid neighbor is not a floor, skip this one. So it's a floor. We haven't visited it before. So it's the new neighbor, so we put dist neighbor is whatever the distance was to the current plus 1. Because it's BFS, the first time we see something will be the shortest time we visit that. Came from neighbor equals current q dot put neighbor. If neighbor is goal, right, so well, that's not where we want to break, is it? Because then, all right, no, we won't do it there. If we expand it, if current equals goal, break. All right. All right, so if we reach this point, I mean, the things we're running this on, it should never exhaust the queue. Right, we should always find a way to get to a location. So, so then we need to know the next step to take from where we are. That's all we need. So temp equals goal while came from temp is not equal to start. Temp equals came from temp. So just backtrack until you've got temp being the next one after start. And then we return temp and distance to goal. Two things we need from BFS. All right. So okay, so in one iteration, we're going to pick one unknown. So we're going to pick the closest unknown. So candidate equals min of, it's going to be grid dot keys. We map a key to, it's going to be the distance from our current position to the to that key. Well, hang on. It's gonna have to be like k for k in grid.keys if grid k equals 0. We only want the unknowns. And then we map key to the distance to that key. So we take the minimum. Okay. So next step equals BFS from where we are to this candidate. Delta equals, it's going to be basically next step 0 minus pos 0. So this is just the vector, the unit vector. So the command, so direction input equals, so it's gonna have to be, gonna have to map this. So say, so let's have a look. So they said north. North is 1. All right, we'll go with that. 0, 1. Goes to 1. 0, -1 goes to 2. -1, 0 goes to 3. 1, 0 goes to 4. So we take that delta, map it to our direction input, and then we do int code dot put input direction input. Is that right? Then we just wait for the output. Result equals int code dot get output. Okay, so what do we do with that output? If it's 0, it hit a wall. Okay, so if result is 0, then it's told us the only information that's changed is that whatever's in front of us is a wall. So we say grid next step equals a wall, which was 2. Okay. Elif. All right, so that's the easy bit. If it says 1, then it's moved 1 step. So either way, it's moved 1 step. So it's else pause equals next step. So we're now standing on next step. So that means grid of where we're standing now must be floor. And for neighbor in get neighbors pause, let's just initialize everything just in case. So it'll be grid neighbor. And then what else? If it's a 2 specifically, then we found the goal. If result is 2, goal equals pause break. So I'll break out of this while true loop. I haven't tested any of this. Should I try running it? Kira -1, 0. Yeah. Came from temp is not equal to start. It says there is no came from for -1, 0. Well, oh, one thing I need to check. If grid neighbor is not equal to 1, there is one exception here. We're allowed to step into an unknown if it's the final step. So if neighbor equals goal or that. Oh, no. If neighbor is not equal to goal and if it's not the goal and it's not a floor. Tuple and int. Next step. Just take the first parameter of this. Okay, it ran. Alright, so finally, we have a goal. So we want to print BFS from the start to a goal. Just take the second parameter. That should be the distance. 298. Correct. And just turn the AC on. Alright, you quickly repair the oxygen system. Oxygen gradually fills the area. Oh my god, this is exactly it. Faster than light. Oxygen starts in the location containing the repaired oxygen system. It takes 1 minute for oxygen to spread to all open locations that are adjacent to a location that already contains oxygen. Diagonal locations are not adjacent. Suppose you've used the droid to explore the area fully and have the following map. So in this example, all locations contain oxygen after 4 minutes. How many minutes will it take to fill with oxygen? So we're just trying to find the furthest point from the goal. So we could just run BFS a bunch of times. Right, well, the first step is to run this exhaustively. So we don't want to... So we say oxygen equals pause, but we don't break. Just do it as normal. Okay, so here, candidate, so if all grid if all v is not equal to 0 for v in grid dot values break. Right, so we should just exhaust the whole thing now. All right. So that means there are no unknowns now. We've completely surrounded by walls. So we could just run an exhaustive. Let's see what it looks like. Well, that means we can just exhaust. We can just do int. So we have the maximum of the BFS from oxygen to a location. Just take the second parameter here. For P in grid.keys if grid P is 1. It's a floor. So we're taking the floor which has the highest BFS distance. Now this is inefficient because you're running BFS over and over again. What you should be doing is one flood fill. Can't be bothered to do that. So let's run it then. Aim from temp is not equal to start. What's happened? BFX from oxygen to P. P in grid.keys. If grid P is 1, that means it's a floor. It could only be a floor if we've actually found a way to get there. So what's happened here is we've not found the goal. So goal is temp is none. So goal was never initialized. So we never found a way to... So basically this queue emptied and we didn't find a way to get to that location. Oh. Maybe there's one case where you're trying to move to your own cell. Let's just say if start equals goal. Yeah, because then the way I did the came from doesn't make sense. All right, so if start equals goal, return. Return, I don't know, start 0. Three, 4, 6. That's the furthest distance. I mean, that could pretty easily be done without having to do a BFS. Just every time we do BF. Oh. Yeah, but it has to be from the oxygen. But yeah, you can just do a flood fill. One flood fill, which does an exhaustive BFS, but... I mean, the flood fill is BFS. We have BFS staring at us in the face. So if we had a parameter saying no goal... then... yeah, it doesn't matter. Let's see if it's the answer. Just do it without a goal, then it could do it a different way, and just Is it 1 minute per? Okay. Correct. That's it. 15. That was nice, straightforward BFS. 16. Oh, looks like some sort of cryptographic thingy. Alright. Hang on. Okay, your flawed frequency transmission. You're 3/4, 3/4 of the way through the gas giants. 3/4. Okay. Gas giants. Oh yeah, because we're at the gas giants, which are... which ones are the gas giants? Jupiter, Saturn. Ah, so Uranus and Neptune used to be gas giants, but now they're ice giants? Okay. Astronomy keeps changing. Not in my day. Alright. Not only do round-trip signals to Earth take 5 hours... but the signal quality is quite bad as well. You can clean up the signal with the flawed frequency transmission algorithm, or FFT. Is this fast Fourier transform? As input, FFT takes a list of numbers. In the signal you received, your puzzle input, each number is a single digit. Data like 15243 represents the sequence 15243. Okay. FFT operates in repeated phases. In each phase, a new list is constructed with the same length as the input list. Wait, so the... okay. So we've got a sequence of integers. This new list is also used as the input for the next phase. All right. Each element in the new list is built by multiplying every value in the input list by a value in the repeating pattern, then adding up the results. Oh, I'm guessing this is going to be like we have to find a sequence really far ahead. All right. Adding up the results. So if the input list were 98765 and the pattern were 123, the result would be... this, okay. only the ones digit is kept. So fine, even if it's negative. How could it be negative? Oh, the pattern could be... pattern is integers. Okay. When each element in the output array uses all of the same input array elements, the actual repeating pattern to use depends on which output element is being calculated. The base pattern is 0, 1, 0, minus 1. Then repeat each value in the pattern a number of times equal to the position in the output list being considered. What? Repeat each value in the pattern a number of times equal to the position in the output list being considered. So, for the first... What do you mean being considered? Ah, okay, so doing this sum here gives us one element in the new list. And to get the next element in the new list, we adjust the repeating pattern and do it again. When applying the pattern, skip the very first value exactly once. So for the second element... What? So for the second element of the output list, the actual pattern used would be this. Okay. So if the base pattern... But doesn't that mean we should skip the 0 of the base pattern? Or... maybe not, I don't know. No, I think just the second. Okay. After using this process to calculate each element of the output list, the phase is complete, and the output list of this phase is used as the new input list for the next phase, if any. Given the input signal 1, 2, 3, 4, 5, 6, 7, 8, below are 4 phases of FFT. Within each phase, each output digit is calculated on a single line with a... Alright. So the initial pattern is... the base pattern 0, 1, 0, minus 1. Oh, but you do cut off the 0. Okay, so... So you keep the 0 for the purposes of getting the next pattern, but when you apply the pattern, you ignore the first digit. So it's 1, 0, minus 1. Then the next pattern will be 0, 0, 1, 1, 0, 0, but you cut off the 0, so it's 0, 1, 1, 0, 0, minus 1, minus 1. Okay, got it. Okay. Here are the first 8 digits of the final output list after 100 phases for some larger inputs. Computationally, is this going to take a long time? We're talking... each digit... each digit of the new input takes a linear time to process this. So basically, one phase would mean so getting one element would mean a linear time. So getting one full output would be quadratic time, and then multiply that by 100. I think that's all right, but it's quite long, but it's we can do it. Okay. Interesting. Okay, so we just want to sequence equals int x for x in f dot read line dot strip. Okay, so it's a list of integers. So let's make some methods here. So define FFT given an input list, let's say array, and a repeating pattern. We'll want to spit out the new array. FFT operates in repeated phases. Okay. Right, so should I call it? Let's just call it phase. Because FFT describes the whole collection of phases, I suppose. Okay, so how do we do one phase? So we're given a pattern. We so just say new pattern equals pattern 1 onwards, because we need to chop off the indices to work here. So we chop off the first character. And then we're going to do the sum of be sum of, so it's going to be, hang on. So if I is the index, it's going to be array I times pattern I percent length of new pattern. So that should be new pattern. So that restricts to that region for I in range length array. with that sum, then we only take the, so we take the absolute value of it, so it's positive or non-negative. And then we do mod 10 to get the units digit. So result equals list result dot append that. And then wait, so okay. This is not a phase. This is just FFT. So we've got a base pattern, and then we've got pattern equals base pattern. I don't want to change the original. And then pattern to use equals that. So we're gonna have to do this. We're going to do for, let's say j in length, in range length array. Doesn't actually matter what j is. We take pattern. No, this is okay. This is the initial thing. So pattern to use is that, blah, blah, blah. I'll do that. And then after this, we want to change the pattern, expand the pattern. Is there an efficient way to do this? Can we just just temp equals this for x in so what we're using pattern temp dot append x temp dot append x twice. Is that no is that repeat each value in the pattern a number of times equal to the position in the output list being considered? Oh, okay, fine. We don't need to do that. We do need j here. So pattern to use equals, so it's going to be this. So we don't, base pattern, just, we don't need to change that. Just say pattern. All right. Okay, pattern to use is an empty list for x in base in pattern. Pattern dot use dot append x, but we want to do it for j times. So to begin with, j j will be 1. J will be 0. So we do j plus 1 to get 1. And then pattern to use, just delete the first one. That's how we construct the pattern. So the base pattern never changes, but we construct it each time. So it'll start with 1, 1, 1, 1 of each, and then 2 of each, and so on. Okay. Result is just that. Result.append that. Okay. Let's test this out. So we've got a sequence. Or should we just jump straight to the answer? Let's say for in range 100. So we want sequence equals FFT of sequence with the base pattern. So it was 0, 1, 0, minus 1. 0, 1, 0, minus 1. Then the first 8 digits in the final output list. So print dot join string x for x in sequence up to 8. Okay. None object has no length, because we never returned the result. All right, hope it's right. Took a few seconds, but I don't think there's any way of skipping steps there. You have to just do all that. It's too high. Oh dear. All right, let's try input signal. Just this one. Just do 1 phase. 3, 8. 38226158. It should be 48226158. How am I 1 off in that digit? So the first number should be so you should get 4. Should be using 1, 0, minus 1, 0. So I haven't added one of the digits. So how did I get a 3 instead of a 4? Is it the first pattern to use for x in pattern for that in range j plus 1? So when j is 0, to use append X. Just I don't know. Print pattern to use 1 0 minus 1. Oh. You just... Oh, I see. When you use the repeating pattern, you discard the first element, but you still repeat as if it was there. So actually, what you should do is... this. Pattern to use... Oops, I'm on the wrong window. Pattern to use equals... pattern to use 1 onwards plus, so it's as if you inserted it at the end. Like that. You just rotate it by 1. Four eight two two 6158. Okay, that's correct. Okay. We want to do this 100 times. Okay. Correct. Now that your FFT is working, you can decode the real signal. The real signal is your puzzle input repeated 10,000 times. Treat this new signal as a single input list. Patterns are still calculated as before, and 100 phases of FFT are still applied. Right, there's no way we can run this as is. We'd have to we don't need to calculate the full number. We just need... You need all the digits for... So the first 7 digits are the location of the 8-digit message. The number of digits to skip before reading the 8-digit message. Here is the 8-digit message in the final output list after 10 phases. Right, there's some ways we can speed this up. But so if we look at this pattern, you're ignoring, whenever there's a 0, you're ignoring those elements. Whenever there's a 1, you're adding those elements, and whenever there's a -1, you're subtracting those elements. So it's kind of like yeah, but that only means half of them are cut out. That's not that much, but is there, we don't really need to calculate this pattern every time, do we? Can we just, if we knew that, can we just immediately calculate what? We can, can't we? So if it was, if we didn't cut off the first element, let's consider that case first. Then if you wanted the like position, if you wanted well, it doesn't harm us to make the patterns. But how many patterns do we have to make? 10,000? Suppose we could do that. But it'd be 10,000 patterns, so it's gonna be like in the millions. But if we initialize them all, then we'll never have to make them again. Let's try that first. I'm not sure how to speed this up yet. So let's initialize a pattern list. So it's going to be the J determines which pattern you use. So it's going to be... let's say patterns equals that. So n equals length of sequence times 10,000. So they're saying multiply whatever here by 10,000. Wait, so what is that? It's actually 6 million. Bloody hell. That's even worse. Oh, man. Okay. So I think the... I think the fact that it's repeating is important because all that matters is which pattern, which index of the pattern you start at, right? And then the next chunk will have a different sum. Ah, I see, I see. So we have the pattern, we get the sum. Now we're doing this 10,000 times more, right? When we're computing this sum. However, we just have to calculate what it would be like at starting at a certain... Okay, so consider this. In this pattern, we have this pattern, right? But we start from index 1. For some reason, we skip 0. So we start from index 1. And that gets us a certain sum. If we had started from 0, we would get a different sum. If we had started from 2, 3, and so on, we would start from a different sum. Every one of these 10,000s is just going to be one of those. So we just have to compute the sum for each element of the pattern. And then for each of the 10,000, we just recall that value, that sum value from the from that table. Furthermore, that sequence itself is just going to be a repeating pattern, but that doesn't matter so much. So let's say we memorize. This is memorization basically. So we define a method here. Define get pattern sum for a given index. All right. Yeah, I think this will be efficient. So we basically do this sum here. But we want to memorize. So if index in table return table index result equals this, sum of array I times, no, we don't do this, we do no more pattern, no more messing around with these pattern to users. In fact, that was a waste. We do pattern, so it's going to be index plus I don't know why I didn't do this to begin with. Length pattern. Table result equal the table index equals result return result. Okay. So now get rid of all this. This should be faster now even for part 1, so let's try that. Result dot append, so take this out. So it'd be the absolute value of get pattern sum starting from index 1, not 0. All right, try that now. Array I times... Oh, fuck, because you still need... Ah! Because you do actually still need the... Oh, this needs to be per J. Fine. This is because it's going to be different for you. It's different pattern. Okay, fine. Do it like this. So we do actually need... We're using pattern to use, not... But we do use that, so... Get pattern sum 1. Try that. That should still be faster, but it's no, it shouldn't be faster. It should just be the same. We're just doing one sum once. Oh, bloody hell, we get a different value now. Sum of array times pattern to use. So it's going to be index plus I. Oh, because I chopped off the thing, didn't I? So we don't need that. Starting from 1. 440982. 44. 0982. Okay, so we've got the same result. Now, how do we use this? So now, for each of these, we're going to spend 10,000 steps, though. There is a way to speed this up, but I don't know if we'll actually need it. But anyway. Also, these can be stored beforehand. Because they're going to be the same for every iteration, aren't they? So, let's try that. So, patterns equals that. So, it's going to be like this. Put J in range, so it's going to be N. Oh, hang on. But what about the extra? The array is bigger now. Oh no, this is so confusing. This only works for the first few characters, for the first n characters, first n positions. Then afterwards, you're using a larger sequence. But this is really weird. Okay, it's fine. I think basically you need a method. You forget about all these patterns and everything. You just need a method which says, given your position, I want to know if it's the 1 or the -1 or the 0. Because there's just 4. So first you want to find, okay, so we know the length of what the length of the pattern would be. Okay, hang on. Okay. Define, we don't need to mess around making patterns. Let's say define get, so that what we use the pattern for is to get the 1 or the -1, right? Or the 0. And if we knew how many times something's going to appear with the 1, how many times it's going to get the -1, then we'd know how many times it appears, wouldn't we? But that's a different story. Okay. This is basically matrix multiplication, isn't it? We're actually multiplying matrix whose rows are the repeating patterns by but we can't use numpy or something like that because the matrix would be too big. Okay, just continue with what I was doing here. So for so I'm saying, okay, get rid of this. Define get pattern value for a given output index, right, for a given array input index. We want the value. It's going to be as a -1 or a +1 or a 0, essentially. So how do we do this? So if the index is it's basically the output index +1. It's that many repeats of the zeros, the ones. Okay, so the length, so base pattern length equals output index +1 times 4. Right, because of the 0, the 1, the 0, the -1, so okay. Well, let's store this base pattern here. So it's, what is it? 0, 1, 0, -1. Okay, times length of base pattern. So this is not base pattern, this is scaled pattern length. So scale pattern length is going to be that times the length of the base pattern. All right. So the index scaled pattern index equals input index sent scale pattern length. All right. But because we've offset it, we have to add 1. So if we were looking at the first array, we would get index 0 here. But because we want to start from the index 1 in the pattern, we add 1. So we add 1 here, actually, not there. So that's the scaled pattern. That's the index in the scaled pattern. So base pattern index equals scaled pattern index divided by this, essentially. So it was scaled up to 3. Let's say it's scaled up to 3. I want to divide by 3 again to get whatever the index was here. So if for example we had 0, 0, 0, oh, yeah, 0, 1, 1, 1, 0, 0, 0, minus 1, and so on. Let's say we were here. Our index would be 1, 2, 3, 4. 4 divided by 4 is 1, rounded down. So that'll give us the 1. Okay, so that's it, right? We return base. That wasn't that complicated. It took me a while to think about it. Now we don't need to mess around with any patterns. It's pure arithmetic here. So we want get pattern value. So get rid of this. Let's get rid of all this stuff. Okay, so pattern sum equals it's gonna be essentially this, but this bit here is just get pattern value. So the output index is J. The input index is I. All right, see if that actually gives us the answer. The same answers before. What's it doing? 4.098263. It still took around the same time, but I mean, this is much cleaner. No more having to deal with patterns. Okay, so that's the start. So this is quadratic. Now what? I reckon this is more about if we knew this. So, although this entire sequence is going to be millions long, we can calculate all the prefix sums. So we know the sum of every prefix of it. And from that, we can effectively get the sum of every slice in constant time and when we need it. Right? Why would we need that? But because this pattern has got a bunch of ones and a bunch of minus ones. So essentially, you want to so you want to, if this was a whole bunch of zeros and a whole bunch of ones and a whole bunch of zeros and a whole bunch of minus ones, you would want, when you're applying this pattern to the array, you would have a contiguous subarray where you're just adding all those elements together. Similarly here, you get a minus here. So you don't need to add all those things individually and have to call this every time. So actually we don't need this if we're going down this route. Instead, we should be adding chunks. That reduces everything to chunks, so that eliminates a large factor. Let's try that. So how do we do that? Basically, we would first we need to compute all the prefix sums. Let's try that. So for x in sequence. Hang on. Yeah, but then we need this for every. We need this for every step of the FFT, don't we? Well, we can do that. But it doesn't need, it shouldn't be done here. It should be done here. Okay, prefix sums then. For x in array prefix sums dot append whatever the last value was plus x. So if you want to fetch the sum from index 0 to index 2, say, you would call prefix sums 2. And that would basically include the 2 elements. All right. Let's just see how much longer that takes now. But now we'll use this to speed up the... Okay, not much longer. Right, now we can use this. So we can say... Okay, let's try a different approach here. So we say... So we've got J is the output index. So repeated length equals J plus 1. That's the base pattern's repetition length. So let's start with a base pattern. So base pattern index equals 0. We start with the first thing in the base pattern index, and when it comes to summing the input, we do input. So it'd be input index equals 0. All right. While input index is less than length of. All right. So we're running through the input index. We're adding chunks using this repeated length. So and we're skipping the zeros. So we're actually going to cut out a lot of work here. So if base pattern, so that if the value is not equal to 0, then we do this. So hello, DJ. 15. I did question 15, which was pretty easy, just searching through a grid, which we do so many times in these problems. I'm now on a pretty tricky cryptography one, which involves a sequence which is 6 million in length, and we need to find some way of encoding it 100 times in a row. I think the way to speed it up is to look for sequences of repeated sequences and simplify them. So let's see if that's not 0. We're gonna do, all right, so total equals 0. num repeated equals j plus 1 if input index is greater than 0. So normally we use j plus 1. Get rid of this. But if we're starting, we actually have to use j. Just because of that weird one-off that they did just to throw us off. Okay. That's the num repeated. So we want to get the sum of elements from... So slice sum equals. So it's going to be prefix sums up to hang on. Slice end will be input index plus num repeated, but we have to round down to in case it overflows the array. So do minimum of that and length of array. So that's the slice end. So the slice sum is prefix sums slice end minus prefix sums of the input index. So that's the slice sum. Total, add the slice sum. Okay, and then in either case we want to go to the next base pattern index. Oh, well, we have to actually multiply this by the base. Alright. And then here, move to the next base pattern. The input index is going to have to change, so... So... that is computed no matter what. So slice end will be the new input index. Slice end. Okay, so that's all the things being changed, and so the idea is that we would end up with the total after that. So then we would add abs of the total %10. All right. Hopefully get the same result. It takes a while to compute the prefix sums, that's the problem. But I would have thought it'd be faster overall once we've done the prefix sums. Wait, no, it shouldn't take long to compute it. It's a linear search through the array. Alright, it's stuck somewhere. While input index is less than length array. Index equals slice end. Oh. Ah, no, this logic is not right. This... Okay. First equals true. Can't think of another way to do this. Just do that. And say, if... So on the first iteration, we just have to subtract 1. First... num repeated minus 1. First equals false. Minus equal 1. So we just have to cut off that one element on the first iteration. So it was an infinite loop. There we go. 44098263. And that was faster. Much faster than before. So now we can discard that. So now, can we run this on our big pattern? So that is part 1. Part 2. So it's still gonna take too long though, isn't it? But it's... You can see how many iterations we can get through, but it's... No, we're gonna need something else. Just try it anyway. So we've got to start with sequence equals the original sequence, so 650. So here the problem is these... right, whatever. So this is going to have to be multiplied by 10,000. That's crazy. It's going to be too big. And then print I, try to apply. We don't need this parameter anymore. I am range 100, okay. So it's stuck on the first iteration. We have to do that 100 times. Fine. We have to eliminate this 10,000 factor because it's just repeated. Whenever something's repeated, usually there's a shortcut. We can check if it's probably the right answer though by testing against the examples. Let's see. Okay, so use this input. That's taking a while, isn't it? Well, we can try and leave it running, but that's not fast enough. Okay, so now what? I don't think I can finish this right now. I might have to continue next time. Unless I can quickly think of something. So we have an efficient way of using the pattern, so that is no longer... The problem here really is this is going up incrementally linear time. Now, we shouldn't really need to have to do that. Well, we kind of do... No, it feels like we do, because... Okay, go back to what I was thinking earlier about this 10,000 business. So... Hang on. Ultimately, we still need to make an array of millions long eventually, because don't you need that for the next iteration? Like, there's no way you could avoid that, could you? Well, using the... I have a sort of idea, but it's a bit weird. Right, I think it's something to do with... Alright, so... This huge sequence is repeated 10,000 times. No, I thought I had something, but the base pattern repeats also up to that many times. So like there could be like 6 million zeros in a row. Which is weird. Excuse me. Should we just at least run it on 100, like we were just doing now? Wait, but we still need to do the final bit. So once you've got the... Okay, so you need to take the first 7 digits of the input. Okay, so the offset tells you the location of the 8-digit message. So message equals, so it's going to be this, so it's going to be offset plus 8. So if I run this and let it run to 100, we should hopefully get the answer. That means it's correct. Oh. Oh, I see. Okay, just let it run to 100. That will mean our logic is correct. We just need to find a way to reduce it by a factor of 10,000, essentially. So we know what the offset is to begin with. So we know where in that message, in that sequence is the message. So can we get away with not computing the millions of other digits? It's tricky because you use all those digits to create the next iteration of the message. But... ugh. This is a tough one. How do people find it? Let's have a look. 16. Yeah, it's harder because there's more people who did silver but not gold. Even though it looks like it's easier, but it's just because more people got stuck on silver. And part 1 was fine. Took about 20 minutes for them to solve this. Up to an hour. Alright, if I get this right, then I might just call the stream here and continue next time. Alright, let's see. This is just for the sample input. So the real input is just massive. 20 minutes is a long time for first done. Yeah. Last advent of code, I think 1 or 2 of the problems took up to about 40 minutes to an hour for some people to solve. Those are really hard. .00442, is that what they have? No, it's not. Damn it. So it's not even correct. It's slow and incorrect. Alright, well, we've got a lot of work to do next time. Oh, fuck. We're using the wrong sequence. This seq is the result of previous part before we reset it. That could be it, or it could not be. Could be another problem. Let's test it. We're using the wrong seq. Okay, now we've reset seq. Now we're using that seq. Alright. Hello, lazy aseku. Alright, so I'll just wait for this to run again. Look at it go, yeah, it's racing through those numbers. This is really... There must be some really clever trick to this. FFT, I think it's a reference to fast Fourier transform, which is not actually what we're doing here. But it could be a hint. Oh, it's... I can't remember. It's been a long time since I did Fourier transforms. It's more of a electronics thing, but alright. I think that's enough coding for today. Mostly. And Come on. I'm gonna be thinking about this all night long if I don't solve it today. Which I'm not planning to, so. I'm just wondering if you could do something clever with matrices, but I don't think so. It's like you'd have matrices which are millions in width. Oh, man. What? I got 00442480 again? How? But it was using a different sequence. So it should have been different. No, it's the same sequence, different offset. How could it be the same? Oh man, what? They could have given us a simpler input than this. So I don't have to wait forever for it to run. What on earth? So print my sequence equals FFT sequence. Four, 462. Nope, that's nowhere near what we're supposed to get. It's 10,000. Yeah, but I mean, these numbers don't matter. How could it be? Is FFT always using arrow and not something else? Yeah. So what for the first answer we get 2, 4, 4, 6, 5, 7, 9, 9. Wait, what? No, that's wrong as well. I've broken part 1. No, I haven't. That's for the bit the example input. Alright, we'll worry about this another time. It's just broken in many ways now. I mean, if I were back working in the office, I would end up staying late into the night just because you never want to leave your code in a broken state, but not anymore. All right. Well, that was day 15 and partial 16. I guess I might be back on tomorrow. Or I might take a break because that's been like 4 days straight of Advent of Code. And it's not exactly Christmas, so I don't have to punish myself this much. Yeah, I'll have a think about this in the meantime. Thanks for stopping by, Lazy. Are you doing anything Advent of Code or anything like this? Do you know what Advent of Code is? But we've got another coding competition coming up, which is coding game. Oh, but I don't think it's the good kind of competition. I think they're doing the boring one, which is the you just know about it today, and definitely will try that out. I think it's like the best educational resource for programming there is now. Like a lot of these big corporation sites have gone not great. They've gone like you can see from the front pages they've gone into marketing. They used to be great. They used to be the kings of learning algorithms. Now it's this site, all made by one guy who really has enthusiasm about his site, and he doesn't want to turn it into this. That being said, I do like coding game. It's great, but you can see these sites are becoming very corporate. I can't even see from here without logging in. I can't even see the problems. It's just a lot of advertising for companies and stuff. Anyway, welcome back to Advent of Code 2019, day 16. I'm in the middle of day 16. I don't normally like to leave things unfinished, but sometimes it happens. So, quick reminder, we have this encryption algorithm, sort of. Well, it's not even encryption, it's well, yeah, it is encryption. We solved part 1, and then part 2 is sort of the same, but you have to do it for 10,000, a sequence that's 10,000 times the size, but it's repeated, which is probably where the trick is. Now, I think I've been thinking about it over the past couple of days, and I think I have an idea for how to speed this up. Before I do that, though, I think we were getting a wrong answer. So that needs to be debugged. So let's see. So here we've got 10,000 sequences. So initial sequence is that. Base pattern is that. So that's part 1. We just, when we run this, it goes through them step by step. Okay. And then part 2, we start a new sequence. Offset is in there. And then we want to get the message from the sequence, so do we get the correct answer for part 1? 244. Well, this is... What's a different input sequence? Alright, how about we just go back to part 1, make sure it's still working. Input signal. Okay, how about this? That 24176. 24176. Okay, that's correct. So it's still working for part 1. Part 2. Puzzle input repeated 10,000 times. Oh. Oh, I know what might be the issue. That. Can't do that. No, no, no. It's creating reference copies of the list. So if I change something later in the list, it's going to affect all 10,000 blocks. Yeah, so... How do you... What do you do here? How do you make... Do you do, like, this? Sum of... Can you do a sum of lists? No, 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 no. Okay, how about this? Sequence. I don't like having to do it this way. I'm sure there's a... Should we just... Let me just Google this. Python. Concatenate lists together. Just take a sequence of lists and put them... Concatenate them together. It's reduce, isn't it? You want to reduce... Try using reduce. It's not something I practice much. Sequence equals reduce. Do we have to import reduce? Reduce. The function. So is it just going to be... You can't just put plus operator. Let me Google this. Use reduce to concatenate lists. Alright. You just have to write an explicit lambda. I'm sure there was an easier way of doing this. Extend? Oh, no, no, that's not what we want. Star operator, yeah, don't do that, because that's not actually a proper... Okay, reduce, here we go. I have to log in to read about reduce? Fuck off. I can see... Roughly see what they're doing. Reduce lambda x, y, x plus y. Okay, just do it that way then. Lambda x, y goes to x plus y. And then we want... Hello, DJ. I've just started on the... Well... Just continuing from where I left off last time with problem 16. I sort of have an idea how to do this now. First, I need to get it the correct answer, even though it's slow. Then we can think about speeding it up, so... reduce. So we want this. Reduce that. Okay, try that. Now it's going to take ages to build that sequence, but once it does, it should be faster to do each one. Well, it's about the same. We'll just have to wait for it to hit 100 then. No, because we don't have the answer for this one. Stop. So we want to try this one. Okay. Okay, so just wait for that to hit 100. See if we get the right answer. Alright, and hang on, stop. I should print sequence as well. No. Print. Yeah, the sequence is too big. Just leave it as that. Okay, so let's let that run. So in the meantime, see what's wrong with this, if there is anything wrong. So prefix sums equals 0. Thing is, we still have to do 6 million operations each time. That's still too much. It's almost 1 billion. It's doable, but talking, it's going to take several minutes to, I don't know, up to an hour. Depends. This will have to go. Would be replaced by smarter method. So this 0044. No. Getting 0044 again. Why have we got this one? I don't think this reduce is actually doing what we think it's doing. No, it's doing the same thing. No, it's not. It's creating a new copy each time. I don't know. Let's test this out then. I don't know. So, sequence equals reduce. Let's make this 1, 2, 3, 4. So that gets a sequence, and then do sequence 0 equals -5, let's say. Print sequence. So only the first element should change to -5. Oh, this is really big. Yeah, okay, so that's safe. That it's not changing any others. Alright, well. So that is the correct sequence. And part 1 sort of shows that this method works, FFT. So the problem is probably in this offset message thing. Let's have a look. Offset. Sequence up to 7. So the first 7 characters. Of the original sequence. Do I have the correct offset? I'm gonna check all these things now. Two, 4, 4. Oh no, that's part 1. 303673. Yeah, okay. So with that, we skip. Let's stop running this. We still run this 100 times. So we get the final output. Offset to offset plus 8. I don't actually like this method though. I mean, we can change it even though it's kind of wrong. But it's working for part 1. But how could it be working for part 1 and not part 2 if it's the only thing that's changed is a bigger message? Is there anything that would actually change here? don't think so. I don't like this first equals true nonsense. Can we just not do that? Num repeated equals mo. Num repeated? What does that even mean? What? Maybe we should change this. Oh, num repeated means number of times a specific one of these gets repeated for each each subsequent item in the input array. There's got to be a better way of doing that though. Let's define get sum effectively. What we're trying to do is get dot product, right? So get dot product for the jth no, we don't even need it for a given num repeats no. Yeah. Pattern repeats. So given a number of pattern repeats, an index to start from, and the array is fixed. So we've got a method which tells us the product for a given number of repeats and a given index. Okay. This is basically this logic, I guess. We can extract it for now. Total equals 0. First equals true, while input index. Okay, take these out. While input index is less than us. So num repeated equals that plus 1. And if it's the first iteration, we just subtract 1 because we're starting from a different index. So actually, whoa, take that out for now. So this starts from index 1. So it'll be the input index plus the number of repeats across the length of the array. So the sum oh, wait. This isn't correct. Not always. Oh no, this is fixed by this, so... no. We don't need this at all. So on the first iteration, there's just one of each number. So if it's... so here, this becomes 0. And then it'll be input index plus 0, so it'll still be 0. Slice end. So the slice goes to the end. It goes just is a null slice. If pattern repeats is greater than 0 and the pattern we're looking at is non-zero, then we add the sum. And then we go on to the next base pattern. And we cut the slice. Alright. So if that might have fixed it. Now we want product equals get dot product of pattern repeats is going to be j plus 1. Let's call it dot product so we're clear. Dot product. Let's try that now. Hopefully we get the same result for part 1. All we did was move stuff into a method. What's this? Okay, well... it's stuck. While input index less than length array. What happened to... okay, get rid of part 2 for now. Alright, it's stuck. So when you do one operation of this, we've got pattern repeats, so so for j equals 0, we want number repeats equal 1. Oh. Oh, damn. Hang on. Alright, if it's the first iteration, we should just... Alright, so block size equals pattern repeats. If it's the first iteration, then we just have to subtract 1. Oh, we never returned anything. That's also a problem. Alright, try that. 244. I think that's correct. Well, we've got to make sure. So for our input, four four zero. 440. Okay, so that's correct. And if I run part 2, it's going to be the same speed as before, probably. That's fine. Okay, it takes a while to do the reduce. But the reduce needs to be done. So how long is it going to take when we've got this massive thing? Oh, it's doing it for the large one. Well, that's going to take too long. I don't know how to solve that issue, but start with the small one. Alright, well, we can see if we get the right answer, but we haven't changed much. Now, there's got to be some major simplification here that I'm not seeing, because even doing this, creating this massive sequence, takes too long. There's 10,000 times 6 million. Let's just try and get the answer correct first, even if it's too slow. But as far as I can tell, you need that whole array. How can you skip it? Because you're taking a dot product with a repeating list. So even though you know what part of the list you care about, just these 8 characters, somewhere in the middle, even though you know that, you still, to get even one character of that, you still need to take the whole sum across the whole list, don't you? Or... Oh, wait. But I think... Actually, you don't, because... Oh, okay, hang on, I'm getting an idea. For each of those 10,000 blocks, there's only a small number of possible different sequences it could be, because it all depends entirely on the index of the repeating pattern you're using. So, you don't need that entire array. It's still confusing though. How do we put this all together? We need lots of sub-methods. Okay. So the first thing we need to do... Well, let's see if we can get this working. Still wrong. Why do we keep getting this 0044? What is that number? It's not the right number, but it's consistent. Consistently the wrong number. What else? So it works for small sequence. It doesn't work for the big sequence. 0303. I wish they give a simpler example here. How can it be working for part 1 and not part 2 in this case? But the only thing we're changing really is making this bigger, although we're doing it in a weird way, but... So we've got really big J values. That's one of the differences here. Can we... What else? What else could be wrong? Maybe it's just as simple as we're using the wrong variable name somewhere, we're referring to the wrong thing. This is a bit of a mess here, bro. Prefix sum, so that's computed here. Oh, 0306. Puzzle input repeated 10,000 times. So we keep the offset as part of the input signal. We don't take it off. Do we? Oh. Why couldn't they give us a simpler example? Zero, 1, 0, -1. We never changed the base pattern, right? I'm running out of things that could have gone wrong. Plus equal. Just bracket that. I don't think it matters. Just put this here. Oh. Um, I don't see anything wrong. What the f- Oh no. Oh no. That should be message, not seek. It was the most simplest. Oh, I bet that was it. Let's try running it now. That. Why was that seek? Should have been message. Message is the extraction. Wait. We don't even need to do that. You literally just print message. We've got the message. There. What was that? Let's try this now. Right. If this is the correct answer, then we are one step closer, but still, I don't see a complete way to optimize this yet. But if we get the right answer here, then we're on the right track. And then the next step we can do is change this to be generic index. That would be useful. This is a really hard problem. How fast did people solve it? 20 minutes up to an hour, 8 minutes. That's quite a long time. Okay, so we need to think of everything. We need to think in terms of blocks. So we don't have one giant input list. Instead, we have 10,000 blocks. Okay. And eight, 4, 4, 6. Correct. Okay, so that's fine for the example. Of course, if I try to run it on the full thing, it's going to take absolutely forever. I mean, this step alone takes too long. It's 10,000 times 6 million or something. So yeah, clearly we can't do that. So instead, we have to... Now, how could we represent our sequence? We could represent it as a map. No, like 10,000 item array, and each item is one block. So, So... Before I do that, though, I want to change this method to use an offset. So, oh, offset equal offset. All right. So the base pattern index, what will that be? Basically, it will be so each of these blocks will be num repeats long. So it will be so the number of steps we move along in this pattern will be offset divided out the pattern repeats that's how many steps we move along. Percent 4, and then that's because we go around in a circle. Or specifically, length of base pattern. All right, so that's where we start. So if offset is 1, then in most cases this is just going to stay 0. But except for the first case, when pattern repeats is 1, it'll be 1 divided by 1, which is 1. So we'd actually start here. That's useful. Okay. Then, the other thing we need to know is initial num repeats. This will be different from all the rest. This will be basically it'll be offset minus, so you divide out all these blocks and just whatever's left, that's just how far we go into the actual block of repeats. So that's the initial num repeats. Shouldn't be 0, because if it was, we would have... Oh no, it could be 0. Yeah, I mean, in the case we're saying offset is 1. So we start here. So initial num repeats, it's going to be 1 minus 1. But we don't want that, do we? We want... Hang on, no, this is not right. Oh no, I'm using my terminology wrong. It's not that. No. It's this, isn't it? That. Offset divide out modulo the pattern repeats. No, it's not that either. Wait, what is it? The answer to this should be 1 for this case with offset equals 1. With offset equals 0, I mean, with offset equals 0, it should be pattern repeats. So it's going to be pattern repeat. Ah, of course, pattern repeats minus Is it that then? So if offset is 0, that will be 0. So just be the pattern repeats, the full thing. If offset is 1, it will be normally you subtract 1, except when offset is the same as pattern repeats, i.e. if pattern repeats is 1, offset is 1. So this actually becomes 1 modulo 1, which is 0. Then it would still be pattern repeats. It would just have moved on to the next index. Okay, I think that's possibly right. So base pattern index is that, initial number repeats is that. So here, if first, no, we don't do this. Block size equals initial. No, okay. We basically do this, but we don't do that. We do equals initial number repeats. Just it's safer this way. So in general, it's pattern repeats. On the first iteration, it's initial. Okay, and then we don't ever do that again. And then we just use that all as normal. So the only thing we should change here now is just have an offset of 1 always. Alright, we get the same answer. So it's going to be, we need 244 as the first number. Yes, and then we'll see if we get it for the second one, but we probably will. Okay, so that's generalized. And now that's good because we may need to do lots of different offsets for different blocks. So that method is it efficient? It's efficient for, not for the whole array, but if we were to split our array into blocks and just treat this as running on a block, that's efficient. Like, I don't think you can speed that up any further. Can you? No, probably not. Like, you need to look at the whole array to be able to compute the dot product. That's, unless you do some matrix algebra of some sort. I don't fancy doing that, but I mean, that's kind of what we're doing. Just doing matrix algebra from first principles. The next thing we want to do is just change this to be a... Well, we'll figure this out. Okay, that's right. Now, instead of one long array, I want this array to be a concept which has 10,000 items in it. Or or just some number of items in it. So sequence is not this, it's this. Oops. That. Alright, don't worry about part 2 for now. So it's a series of blocks, and in this case it's just one block. And we want to produce a sequence of a similar form. And then here we just want to get from the first one. Okay. Now the good thing about this is that you could have this same thing in many places in sequence, like say 100 like 100 places, but it wouldn't be replicating 100 different copies of that, separate copies of that initial sequence. It would actually be passing them by reference. So you'd only be storing 10,000 pointers, and there'd be many duplicated sequences, I would assume. Okay. Now this needs to be changed, so call this a sequence, but it's actually a series of blocks. Oh, prefix sums is different thing now. Damn. Can't really do much about prefix sums. Well, for X an array, do we want prefix sums for the individual? Prefix sums will have to be a hash table here, because otherwise we're trying to make a really confusing list. So prefix sums is table which takes the block number in this sequence it's just a table for now. So it's going to take a block number, starting index, and an end index. Or, I don't know, it could be this. I'll just do what we did before, but 0, 4 in range, length, sequence. So for each block, we create one separate prefix array. And then this time, for I block in enumerate sequence. So for each block, and then we do this. So for X in block, prefix sums dot append. So it's going to be prefix sums I dot append, not offend. Prefix sums I, the last one, plus that number. So it's just going to be replicate what we did before, but one for every block. Result. That's a separate thing. Well, result is the new sequence, so it's going to be just, I guess, this for in range. Let's get some numbers in here. Num blocks equals length sequence. Didn't we already have something called num blocks? Block size, different thing. So okay, result is that. Alright, so that handles the prefix sums, I suppose. Get dot product for a given oh man, this is so confusing because how are we gonna for now, it's just this code will just assume there's only one block, so we're just doing it as if there's just one block. It's gonna be block num. Let's change this to, because block is confusing, change this to run size. That's like a run in poker, where it's not even the correct term. 3 of a kind or something, that's not a run. A run is where it goes 2, 3, 4, 5. Whatever, we'll call it run size. Block num. So here, we just use sequence block num. Okay, and then we just use that instead. So always use block num here. So here we're doing for block in sequence for each block. We're just working on each block individually, and they're all going to be basically the same thing. For j in range length of block, we run this get dot product. We need a block num, so it's going to be actually we need a block. We don't need a block num. Just pass the block in. do need a block num. Damn it. Because then the prefix sums doesn't make sense. Okay, I. For j in range, so it's going to be length of sequence I. Expected type list got int instead. Result. Oh yeah, because result is now that. So it's going to be result I. This could go horribly wrong. Alright, try it. No. Okay, it worked. Now, it's not actually correct for more than one blocks because I don't think we've accounted for the offset changing. But let's see how fast it runs, even though it's wrong, because that'll give an idea for the number of operations. Well, this is wrong. Hang on. So sequence equals... So it's going to be, this time, we use the same. So it's going to be, we use copies. So pass by copies. So now that should be, and here we want the first. Oh, that runs a bit faster. All right, and then the message is going to be different. It's going to be like, so we're going block num equals it's going to be offset divide out the number of length of sequence 0. So just divide it out by how many of those we've got. So then we'll use that block num. Offset is going to have to be percent equal that. Okay, and then take the messages. Okay, so this should be wrong, but it runs faster because we've got copies. Still, though, it shouldn't run faster because result. I don't see why it would run faster. Alright, we'll see. As long as it's correct for the first number, 244, because the second one, we need a bit of work here. Why would this be faster? Because it's just the same sequence, except it's now 10,000 blocks instead of one contiguous sequence. I suppose that's easier to work with, but still. Five, 4, 7. Yeah, it's wrong because we're not changing the offset each time. So when we access a different block, so offset starts at 1. So offset is 1 to begin with. But for the next block, it's actually going to be different. im range num blocks. So for j, so after this, well, offset is actually 1 plus... We don't need to set offset equals 1. It's actually 1 plus the length of a block, isn't it? No. 1 plus is going to be... So I starts at 0, so we want I times length of sequence I. If we've moved that many blocks, we rotate through the repeating sequence, like through many iterations, but the number we move through, the number of individual elements we rotate through is going to be like, you got 1 for every item in the block, but then you did that I times because we did that many blocks, so... What's this? Block num, yeah, okay. That could return the right answer now? I don't know. So let's think. We are looking at blocks. No, it's wrong. It's not the right answer because we're localizing to 1 block. That's not the full dot product. The full dot product needs to be... It's a bit more complicated than that. Well, anyway, it's something. It's correct for part 1. It's not going to be correct for part 2. Because we're just doing the dot product of that 1 block with the repeating sequence. So actually what we need to change is... Oh, man. I don't even know how to do this. We're going to have to overhaul this method. I don't really want to do that now. I might not finish 16 today. How is it? Let's have another look at the site. I mean, can it really be this complicated? Let's think. The principle of dot product is not complicated, but the problem is I'm trying to do this all with code and I should really be sketching diagrams and stuff, but it's not easy to do that with Microsoft Paint. So maybe I need another break from this again, and I will actually get some pen and paper and work this out mathematically, and then come back to the stream and try to replicate my diagrams in Microsoft Paint. And try and finish this. I feel like with a diagram it might not actually be that complicated. It's just trying to juggle so many of these things in my head, blocks and inner blocks and all this stuff. As long as we keep it working for part 1. This doesn't work for more than one block because it's still localizing to that one block. It's doing that dot product with the repeating sequence and replacing those elements. That's it. What it should be doing is taking the dot product of the repeating sequence, the blocks, and then replace them in that block. Now, every block which uses the same offset is going to end up looking the same, isn't it? Therein lies the shortcut, because if you have one block where you start at offset 1 in the repeating sequence, and the next block also started at offset 1, you're doing a repeating sequence against all the blocks, so they're going to end up with the same result. So really, we just got to find out what the sequence of offsets are. So the first offset is 1. The next offset, well, that depends on whatever this number is, doesn't it? This number here. Length sequence I. So you want to compute what? So it's 1, and then it's 1 plus this, and it's 1 plus this, and so on. You want to find out what that sequence is until it repeats. That's the first step. And it's that sequence is going to be at most about 600, right? Because length of sequence is about 600 in the worst case. So that's a small sequence. Once you have that, you only have to do 600 of these instead of 10,000, because for a given offset, you compute this, and then you update in your result, you put that answer not in one place, but in every place where that offset would be replicated. So for offset 1, if there are, I don't know, 1,000 different places with offset 1, because it's a repeating sequence. So, oh man, we have so many repeating sequences. I don't know which repeating sequence is which. Let's say the offsets went 1, 47, 2000, 1, 47, 2000, 1, 47, 2000. So, okay, so you compute so that means starting from the first block, every third block is going to be the same in the result. So you compute it for offset 1, you do this for offset 1, and note that you should be not using block num, but the whole sequence. That's why this is wrong. And then every third, whatever that answer is, every third entry of result, you set that equal to this, so you don't have to compute all this again. So one computation of get top dot product takes a very long time. We're talking like, in the worst case, like 1 billion, but because we're ironing out these sequences, it should be smaller, I don't know. The point is you don't have to call this so many times. So we need, get prefix, the prefix map, okay, we don't need this two-dimensional array of prefixes. Prefix sums should actually be some sort of, I don't know, memoized method which computes prefix sums in constant time. That can be done even for sequence of blocks, because I don't see any reason why not. So that has to be changed. Then we'll be able to find a prefix sum between any pair of indices in this whole virtual array that we're not actually storing in memory. Alright, so that's the first step. And then this would need to be changed to use not block num, but the whole thing. Yeah, block num doesn't even make sense here. You're computing a dot product with this number of repeats, this offset, with the whole array. That's what this does. Block num shouldn't even be a thing here. That should be length of the whole array. Should I just make some notes here? Just in case I forget. Tood. Prefix sums should be method to compute sum across entire sequence. What's the other thing? Get dot product. Get dot product should use whole sequence instead of block num. So that relies on prefix sums existing. Otherwise, it can't compute those run sums. And then compute sequence. Don't, if I use seek, I'm gonna get confused with the other seek. Sequence of offsets and to avoid duplicate calls of get dot product. Okay, those three things in that order, because you need to do these in this order, might be the answer. Even then, though, we're still talking about millions to possibly up to a billion operations, but at least that's actually doable within, I don't know, an hour. I'm guessing, though, because of all the blocks of zeros and ones, because we're speeding up using the prefix sums, I'm guessing... Like, think about it. For really high J values here, for really high repeat values, it's going to be very quick, because you're actually just doing one huge sequence of ones. So that's just one big prefix sum, which we already store in our map. So that should be quick for high numbers of repeats. For low numbers of repeats, that's the bigger issue. For low numbers of repeats, that's where we are doing... But we're not... We need to identify... mean, if two blocks are the same in this sequence, which is going to be the same, which is going to be the case often, then you wouldn't need to... So we need some sort of map which keeps track of which ones are the same. Because if we knew that, then we wouldn't have to compute another dot product for the other block. We just use the same answer. So sequence needs to not only be... So what if sequence, instead of being a list of lists, it's a map which maps a block, so i.e. a list of integers, to all the locations in the sequence that you can find that block. Now, if that way, so to begin with, it will literally be the input, this input here, as the key value, and that will map to the full range, 0 to 10,000. Like, that is replicated everywhere in that block. If I did it that way, then in this get dot product, we would only need to compute what? So you got this notion of local dot product and global dot product. Local dot product is where you just compute what the contribution of that one block is. And ultimately you want the global. But the global will just be kind of like the sum of... If all these blocks were the same, then you would just go for one of these and just multiply it by the number of times it's repeated, right? Okay, I've expressed too many ideas here, but okay, one last thing to do. Sequence should be a map from blocks to indices where this is repeated. All right, I'm gonna do all the figuring out offline. I think it's something like this is really complex. It can't be this complex, could it? I'm not seeing a trick to this, but I am surprised that the stats don't seem to indicate it's as hard as I'm finding it. I mean, okay, there is a lower ratio of gold stars here to silvers. But still, quite 9,000 people solved both parts. I don't know. Alright, maybe when I write this on paper, it'll become clearer. Welcome back. It's been a while. About a month, I think. I sort of left a bit of a gap. I kept meaning to come back to this, and I kept putting it off. But we are still on problem 16, and should be able to finish it off now. So, I was going around in circles with 16, not making much progress with part 2. I was definitely going down the wrong path, and I realized it at the time, but I mean, I needed to refresh my head, look at it from a different angle. And I kind of did, so let's try and reason that out now. Day 16 taking a whole month. Yeah, well, I only actually looked, even though I said I was going to look at it before, I only actually started looking at it today. I just procrastinated for a month, basically. Just get my coffee. So yeah, I'll probably just do 16 this stream and not anymore. I don't know how long that'll take. Because then I need to stitch all those hours of me banging my head against the wall together in one massive 7-hour YouTube video. Yay. Not that anyone's ever going to watch all that, but... It's for, okay, so it's for posterity. Let's remind ourselves. So we've got this, not 17, 16. This whole frequency transmission thing. It's a bit of a trap because it's sort of indicating if you don't actually look at your input, or you just look at the size of the input, but not actually look at the individual digits of your input, you would think that you're supposed to actually fully transform the entire 6 million long message each time. And you would be correct in thinking that, because for a general input, you would need to do that. I don't see any way around that. It's like every element. So you do this FFT process 100 times independently. Each time you do one iteration of FFT, each new element of the list relies on a sum of the entire list. So you can't get away with skipping stuff here. You would actually have to compute all 6 million every time. So for the general case, this is basically impossible in a reasonable time frame. I'm talking like trillions of operations. And that's what and all the optimizations I was doing before was getting closer, but I don't realistically see it getting anywhere. Anyway, when you actually look at the input, see these sample inputs, even these sample inputs are misleading. If we look at the actual input they gave us, this one here. So they said the first 7 digits of your signal represents the offset. So that's what position in your list you're going to use, right? So we look what those 7 digits are. 1, 2, 3, 4, 5, 6, 7. So 5.9 million, basically. Well, our list is already 6.1 million or something like that. So it's almost right at the end of the list. Okay, so that's a key property of this input, which is it's not in the middle of the list, it's not near the beginning of the list, it's right at the end. Why does that matter? Well, let's draw a diagram. Let's get paint graphics up. And I'm guessing everyone's input is somewhere towards the end of the list. Oh, forgot to put the music on. I'm gonna have to find some new no copyright chill out music. I can't keep using the same YouTube video over and over again. All right, so all right. Oh, it's not even playing. There we go. Okay. So, paint. Can make it a bit thicker. This calligraphy, just like a marker. No, just like a normal, just a pencil. But okay, brush is the right. Yeah, okay. All right. So, what do we have? We have a sequence. Okay. And it is of length 650. Right. But they're saying you actually construct a larger sequence, which is this 10,000 times. Okay. Alright. So the whole list, if you just forget about the fact that there is repetition here, if for all intents and purposes we just have some list which is 6.1 million long. 6.5 million long. Okay. And I was tempted to conserve the property that there's repetition here, but you don't need to do that because, you know, in the next iteration that will no longer be true. So just forget about that. It's now a list of a random assortment of digits, 6.5 long. Now, in one iteration, we go element by element, and for one element, let's say index I, we basically do the dot product of this whole list with this other sequence they've given us, which goes like this. It goes zeros, 0, 0. Just a sequence of zeros, and how many? There will be I of these. And then there'll be I plus 1 ones. And then you get I plus 1 zeros. And then finally you got I plus 1 minus ones. So the I plus 1 of each, except you knock off the first 0, I guess, just to remove some symmetry there. Alright, so... And then finally, it just repeats from back to the beginning again. Okay. So, like, example, I equals 0, the very first element, there'll be no zeros. There'll be 1, 1, then a 0, then a minus 1, then a 0, then a 1, 0, minus 1, 0. So you would sum the first element, you'd subtract the third, you'd add the fifth, and so on. Okay. So it would look like you'd have to do a lot of work there. And that's true. But for big values of I, in fact, if I is more than half this list, you actually don't end up using most of these. You never go further than here. So the sequence actually just looks like this. If we're assuming I is bigger than, more than halfway through the list, then the numbers, this 0, 1 chain becomes so stretched out that it actually just looks like this. You got I zeros, and then you've got ones all the way to the end of the list. So basically, you're just summing up the final, like, suffix of the list, including your own element. Like, if I is, like, 4 from the end, if we're looking at this element here, then this will become the sum of that plus the next 3 items, right? It would just literally just be the prefix, the suffix sum of the list starting from that element. That's easy to compute, right? So in one iteration, And we know that we only care about the tail of this list. We don't worry about, and everything in this tail only relies on what's to the right of it. So we never actually have to check that all these zeros are here. So we never actually have to sum in any of these first elements. So that means in each iteration, we only ever need to keep the tail of this list. So we're restricted to the final. All right, so what are the actual numbers here? So it's 5.9 million basically. So we want roughly the final. It's more like 6 million. All right, let's say the final 500,000 is the only part of the list we ever keep. Everything before that we can just discard altogether. We never touch it again. Because the index we want is in there. So in each iteration we only touch this tail and update it each time. Okay. And what do we do in one iteration? We just start from the end, so we work backwards through the i's instead of starting from the beginning, like is what my algorithm is doing. Start from the end. So for I being at the very end, the sum is just the trivial sum, which is just the element itself. And the next one you keep a cumulative total and you add the second from last in and put that in, and so on. No more worrying about periodic sequences and blocks and anything like this. It's just a cumulative prefix sum. You do one sweep. It will take 500,000 amount of effort in one iteration. You do that 100 times. The amount of work you do is 50 million. Now that's still a big number, but it's doable. That's fine. We're talking minutes here, if even that. Clear? Don't know. I guess I'll have to code it and see. That is basically what I scribbled on paper here. Okay. So we go back to the code. So we have code here. Does it still work? Okay, first of all these to-dos. Wow, I really set myself a lot of work, didn't I? We're not doing any of that. If this still works, I'll leave it as is for part 1. Let's check. So I've got the input. Yeah, okay, let's run it on part 1. Okay, block part 2. .4409, is that correct? Yes, okay, good. That's a working part 1. In fact, it's faster. All this stuff I did actually made it faster than it originally was. So I did actually have some good optimizations there. It just wasn't enough to actually crack this whole thing. All right, so part 2, in fact, we're not keeping any of this. All right, part 2. Let's say total sequence equals, just say it's like this. And for do this. Okay, so it doesn't matter if we just construct this massive thing. There's probably optimizations we could do to avoid doing this, but it's we can do it once. So total sequence plus equal so that should just be have like 6 million or so. Right. So we've got our sequence. Now we don't need to worry about blocks anymore. That's our sequence. The offset we extract from there. I mean, just call it sequence. Print the offset. So that should be 5.9 million or something. Sequence. Ah. No, we're not doing blocks anymore. 5.97 million. Alright. So the tail would be... I've got to get the index correct here. So it's going to be sequence minus... So what exactly did they mean by... They weren't zero indexing, so they were saying... They were saying that offset is how many digits you skip before you get to the digit you want. So if, for example, the offset was 6.5 million, then you skip the whole thing and that doesn't make sense. If it was 649999, then you would want the last element. So you would want... Basically, we want minus length of sequence, which is 6 million, minus, well, okay, we can do the other way around, do offset minus length of sequence. Is that correct? So the numbers again. If that was 649999, and that is 65000, and you do that minus that, you get -1. And -1 onwards would be just the last element. Is that all correct? Yeah. So this is the tail, and the element we want is the first element of this list, except we have to process it 100 times now. Okay. That's a good start. And when we actually get the message out, we might as well just do this code now because it's right here. It'll be for x in, it's going to be tail. The first 8 digits, right? Because that's what we've got. So let's just print that now. It will print something. That's after doing 0 iterations. That is the number. Right. 995571. So that's somewhere in there. In fact, we can do a Control F. There it is. Is that the right? 622. Because modular arithmetic. So yeah, it would be there. In fact, we shouldn't really... If we're being really efficient, we wouldn't actually construct that massive thing. We would just do modulo. Should we do that just to be extra efficient for no particular reason? No. We have to because we do need to keep 500,000 elements, so we do need to run through that 650 many times. Don't worry about it. Okay, so now. Take that out, so now we do 100 times, we do this process here. So what is it we're doing? We want the suffix sum equals 0. So we're keeping a running total. So how long is this tail? For okay, so for j in range, so we start from -1, which is the last element. We move backwards. Until we get to 0, which is the same as saying minus length of tail. But we want to actually process that one, so we have to do an extra -1 because we finish on minus length of tail. And we're going backwards, so we -1 each time. Alright, so we're starting from the end. We're saying so suffix sum plus equal tail. Okay. We need a temp tail because we don't want to change tail in place because everything should be using the original state. So temp tail equals none for just an empty tail. All right. Tail j. So we add that element to the suffix sum, and then we put suffix sum into the temp tail in that place. Temp tail j equals suffix sum. So when j on the first j, which is going to be -1, we're just taking the last element and we're just putting it in temp tail. The last element actually never changes. That's a fixed point. And then for -2, well, we're accumulating this sum. So we're adding the next element along here. Putting that in there. All right. So once we've done that, we just say, we just discard the original tail. Tail equals temp tail. So it's about 500,000 amount of work. It's linear time, not quadratic time. If you were to do an actual sum, use the actual sum command for each of these j's, you'd be doing quadratic time. That would actually take too long. So you do need to have some smart optimization. This is a linear time suffix sum. Now what? So that's it. Then we just print the first 8 characters of this. All right. It'll take a while though, but I mean we could print the count where we're at. Oh, it's done. All right, that doesn't look right. Oh, because I'm not doing the right calculation. Hang on. It's not, you don't just add the numbers. Let me go back to the original thing. You multiply every value by the pattern, add everything up, then you keep only the ones digit. Regardless of whether it's negative or positive. So you make it positive, and then take the units. Then you won't have this massive number. Okay, so it's so we keep the sum, keep the whole thing in the sum, but the moment we put it into the temp tail, we want to do absolute value and then just mod out 10 to get the units. So it's only ever single digits. Should actually be quicker now, because then you're not storing massive numbers. 12482 Could that be it? Oh my god. That's right. It only took a month. At this rate, we won't be done in time for Christmas. Oh man. That was a very good problem, and I mean, I knew everything I was doing was overcomplicated. The problems never go into as much depth as I was trying to calculate before, but it's just, at the same time, I just couldn't see what the trick is. The problem was I was hung up on this general case. You got to remember that although the questions in these are phrased as if he wants you to solve the general case for any input of a certain size, the reality is he's often giving you quite specific niche groups of inputs that follow certain properties, have certain sizes, and so on. So, as tempting as it may be to create a general case problem that will solve any input, it's not. Sometimes it's not actually possible. You gotta actually look at the input. So it's not like a lot of these competition sites, they don't even show you the input. You're supposed to provide the program. You upload the program, like Google Code Jam, for example. You upload the program. They tell you what the sizes of the input are. So they'll say, okay, it's gonna be between this and 1 million or something. But beyond that, they won't tell you anything like, oh, the first 7 digits will be this and so on. So you just have to solve the general case, and then they literally run it against 1,000 different randomly generated cases, and that's how those work. This is different though. This is like, you got to tailor your solutions to the input. It's quite clever, and I've been trained not to do that, so I gotta gotta remember that for next time, because this does come up every now and then. But yeah, man, I was going down such a... Could I have even got there with the approach I was taking? I felt like, because I wrote all those to-dos at the end, I felt like it all worked mathematically, but I think there might have been some more pitfalls that I hadn't thought about. But there's no reason to do something more complex when just do what you're asked for and nothing more. I mean, this highlights a very, very important thing that you actually have to think about when you actually work for a company as a software engineer. It's so tempting, especially when you come straight out of university, to want to, make a perfect program that solves the general case, which handles, large scale inputs that probably will never happen, and so on. But the goal You know, the goal of the job is to make money for the company, and you make money by just doing the bare minimum. Always. All these big companies, Google, Amazon, I mean, I worked at Amazon. It's just everywhere. Shortcuts, bare minimum, everywhere. We're never actually making golden products which are actually, from a mathematical perspective, like beautiful pieces of code. It's all held together with duct tape, and it all just about works. We just put in the minimum required effort to make it work, and then leave it at that. That's all that happens. Good enough to make billions, yeah. Yeah, I mean, and of course it depends on the industry. Like, there's some industries like healthcare where the bare minimum is not good enough. Maybe like aviation would be another one where the bare minimum is not good enough, and that's of course a big topic right now. Boeing and all that. So, you know, if you're writing software for aviation, writing software for the medicine industry, you do actually want to write for the perfect. You do actually want to write for the perfect case, the cases that never happen, but they may happen once in a million times. But yeah, if like me, you were just making a Netflix competitor, it really doesn't matter even if the site goes down at some point. You know, people will live without their movies for an hour. Although, if the site does go down, that is actually Sev 1 emergency. So whenever I raised issues in the bug system, I had to choose from a drop-down the severity. There's Sev 1, which is the worst, and Sev 5, which is the least. You know, Sev 5 is just like, oh, this button is the wrong color or something, and Sev 1 is like, you know, the website is down. Or I've seen a Sev 1 in the system, our office is flooded, and we can't get into the office. That was actually a Sev 1. But whenever I were to enter a bug into the system, I had to choose the severity from the drop-down. I lived in fear every day that one day I might accidentally click Sev 1. It's just a normal drop-down. You could just click Sev 1, but then you'd have to confirm. But still, if you were to click Sev 1 and confirm, you would ping every single Amazon employee everywhere in the world, including Jeff Bezos himself. Even if Bezos was sleeping, he would be woken up and have to attend to it. Yeah, I constantly lived in fear that I might accidentally one day do that. And for developers, it's not grayed out. Sev 1 and Sev 2 are grayed out for most employees for that reason. But we developers have full access. We have to. You can't get anything done without having that much power. So it could have happened. Personally fired by Bezos, yeah. I don't know what would happen in that case. I mean, it was obviously an accident, but it's also... You've also cost the company a lot of money. Alright, well... I think... How many hours of... Yeah, we'll just have to leave the stream there then, because I've now got to stitch these videos together. So let me have a look at my stored videos. We've got 2.5 hours, then another 1.5 hour. Four hours. Oh, it's only 4 hours, and then this session was half an hour. Oh, it's only 4.5 hours. That's less than I spend on, like, video games in one session. Alright, well, anyway, I'll still do that. So, Have Into the Code will be back, maybe even tomorrow, 17 onwards. And... yeah, I'll just stitch the video together. I mean, the editing, I don't edit anything out. I'll leave all hours of me just staring into space in for posterity, but it will take hours to actually render. Can take a sneak peek at 17. What is 17? Solar flare. Oh god, Rimworld. Oh, it's an int. Of course, it's an int code problem. Every odd numbered problem in this year, in this month, was an int code problem. Do I remember? Well, we've still got the int code script at least. Doesn't look too scary. Something to do with positioning in a 2D grid or something. Alright, well, I might come back later with what game is in rotation now. Discworld or Rimworld? What do I feel more like? Probably like maybe an hour of Discworld and then just Rimworld all night long. I don't know. We'll see. Alright. See you next time. DJ. Bye bye.